Welcome back. This is section 4.6, modeling with exponential functions. So we're going to look at now how we can actually use some of these exponential and logarithmic functions that we've been looking at throughout the unit to actually model some real-world behaviors and solve some problems now. All right, so exponential growth, we're specifically going to focus on doubling time first. So if we have the initial size of a population is n sub 0, so that's our initial population, and the doubling time is a, then the size of the population at some time t is going to be modeled by this equation. So we take n of t, which is the total population now, is equal to n sub 0, the initial population, times 2 to the t over a, where again, t is the amount of time that is elapsed, and a is the amount of doubling time, or time it takes to double. Okay? Make sure in this case that a and t are measured in the same units. Okay, so like if a is in minutes, then t has to be in minutes. If a is in years, then t has to be in years, okay, because those have to match up to be able to actually substitute into this formula now. All right, so under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in the colony. So we want to find a model for the bacteria population after t hours. So we're going to use that doubling time formula, and that's because I see this keyword right here that our population doubles every 3 hours. Okay, so I'm going to say n of t equals, remember our n sub 0 in this case is the initial population. So the initial population is 1,000. Okay, then we're always going to multiply by 2 if it's a doubling time problem. So it's times 2. And then we're going to do t divided by a, where t is the amount of time, a is the doubling time. Well, our doubling time is going to be 3 hours. So this gives us our a value now. And we want an equation in terms of t. So t is actually going to stay in our equation this time. So this is just going to be t divided by 3. So that's the model now for this particular situation. Now we want to know how many bacteria are in the colony after 15 hours. Well, our doubling time was measured in hours. They're giving us a t value now of 15 hours. So all we have to do is substitute that into our function that we just created. So we're looking for n of 15. That's going to be 1,000 times 2 to the 15 over 3. Now, you could just put all that right in the calculator, just make sure that your 15 over 3 is grouped together in your exponent, or you could simplify step by step. If I do that, I would have 1,000 times 2 to the 5th power. 2 to the 5th power is 32, so we have 1,000 times 32, and that gives us now 32,000 as our answer. Now, always think about your units for these real-world problems. In this case, we were looking for a population of bacteria. This tells us after 15 hours, there will be 32,000 bacteria. And then part C here, after how many hours will the bacteria count reach 100,000? So now we want to know how long would it take to actually get to a total population of 100,000. So we're going to take our original model, we're going to set it equal to 100,000, and we're going to solve for t this time. We've got 100,000 equals 1,000 times 2 to the t over 3. And we're trying to solve for t. So our first step in this case is going to be to divide by that 1,000. So when we do that, we're going to get 100 equals 2 to the t over 3. Remember, now we need to get that t out of the exponent, which means we're going to have to use a logarithm to do that. So I'm going to use a natural log this time. You could use a base 10 log if you prefer. I'm just going to do natural log both sides. And so now remember, we can move that t over 3 to the front. So we end up with natural log of 100 equals t over 3 times the natural log of 2. All right, now we need to get t by itself. Well, we're dividing by 3 and multiplying by the natural log of 2. So we need to get rid of both of those things. So my first step here, I'm going to go ahead and multiply by the 3 to get rid of that. So that's going to give us 3 times the natural log of 100 equals t times the natural log of 2. And then we can divide by the natural log of 2. So we have 3 natural log of 100 over natural log 2 equals t. Now, that is an exact value in this case. Most of the time, though, we're going to want to know like about how many hours would it actually take. So you're probably going to get a decimal for this. If we actually put that into our calculators now and get a decimal approximation, that should give us 19.93. And then again, keep in mind your units here. Our t is going to be measured in hours this time. So almost 20 hours for our population to get to 100,000 bacteria. All right, example 2. So a certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on that island is estimated to be 4,100 and doubling every 3 months. We want to know the initial size of the rabbit population. So notice this time they didn't give us the n sub 0. We don't know what the initial population was. That's what we're trying to find in that first part. So let's think about what we are given. Well, if I use my formula here, we're told that the population is 4,100, but that is after 8 months. Okay, so our population at 8 months is 4,100. And then we also know that it's doubling, which tells us we're using our doubling time formula every 3 months. Okay, so this right here is our A value because that's our doubling time. 8 months then is going to be the T value. And then 4,100 is what the population is after 8 months. So that's our N of T. And we're trying to solve for N sub 0, the initial population now. We're going to say 4,100 equals N sub 0. It's a doubling time formula, so it's times 2. And then our T and A need to be measured in the same units. In this case, they're both in months. So we can just do 8 divided by 3 as our exponent. Now this time, we're just trying to get N sub 0 by itself, so we just need to divide by 2 to the 8/3 on both sides. And again, we can just go to our calculator to do that. So if we do 4,100 divided by 2 to the 8/3, that should give us 645 approximately. So the exact value that I get when I do that we get 645.7. Okay, but remember in this case, we're talking about a number of rabbits, and so we know we want a whole number of rabbits, not a fractional part of a rabbit. And so we're going to round to the nearest whole number. In this case, though, we're actually going to round down just because we know that our population is 4,100. If we round up, then our population would actually be higher than that. So in these cases, you're probably going to want to round down to the nearest rabbit. Okay. All right, now the next question is we want to estimate the population 1 year after the rabbits were introduced to our island. So we're going to use our formula now. We know what our initial population is this time. So we're going to say N of T equals 645 times 2. Population after 1 year. Well, notice here that our doubling time A is in months. So we've got to think about our T value in months also, which means for this one now, our T value is actually going to be 12 because there's 12 months in 1 year. We need our doubling time and our T value to be in the same units. I'm going to use 12 this time. So we're going to have 12 over 3. So now when we do this, n of 12 equals, and now we can just put all that into the calculator again if you want to, or if you want to go step by step, we're going to have 645 times 2 to the 4th. 2 to the 4th power is 16, so we have 645 times 16. And if we do that now, 645 times 16 should give us 10,320. And so that's our population now after 12 months or 1 year. And again, don't forget your units here. Since we're finding a population, this was a population of rabbits. So this is rabbits. All right, now the last piece, I'm going to switch over to Desmos here just to look at our graph. Okay, so we want to look at what the graph of this population increase actually looks like now. All right, so we've got n of t. I'm just going to call that y in this case. And then we have 645 times 2. And then instead of t, I'm going to use x here for my variable. So we're just going to do to the x over. And then our doubling time was 3. Now, notice here, I don't really see anything on my graph as is. Okay, so we got to think about what's going on here. Well, we know the initial population is 645, which means that my y-intercept, that's where time starts, right, at 0, that's going to be 645. So I know I need to actually raise my y maximum now. I'm going to go ahead and make it 1,000 just so I can at least see where we cross the y-axis, right? So there's our y-intercept, 645. That's our initial population. And you can see in this case that we are growing exponentially, right? Because we have the x in the exponent. So this is that J-shaped curve of exponential growth. And we could even zoom out a little bit more. We know after 12 months, we're already up to over 10,000. So if I add another 0 here, right, you can see what this curve actually looks like. How rapidly this population is increasing as time goes on. All right. All right, now exponential growth with a relative growth rate, right? So we've looked at doubling time. Now, what if we know the actual rate of growth of something instead? How do we solve those types of problems? Okay, so we're going to use the formula n of t equals n sub 0, which is still the initial population. Now we're going to use base e, our natural base. R is going to be our rate, which is going to be in a decimal form, just like we did, percentages for interest before. And then t is our time. And again, our time typically is measured in years, but it could be a different amount of time, okay? Now, notice here, this formula is very, very similar to our compound interest when we compound continuously. The only thing that's different now is instead of P, we're using n sub 0. So instead of having our principal amount of money, now we have an initial population, but the rest of the formula is exactly the same. Okay, so if you can remember that compounding continuously interest formula, okay, then our exponential growth formula with a relative growth rate is exactly the same. We just have a population instead of amount of money. All right, the initial bacterium count in a culture is 500. A biologist later, makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. We want to find a function that models the number of bacteria after t hours. Okay, so this time our t is measured in hours. We want to figure out what this formula is going to look like. Okay, so again, we're starting with n of t. We need our initial population. Okay, so our initial population this time is going to be 500, right? So it tells us the initial count is 500, so that's our n sub 0. Now this time, because we're given a rate of growth, we're going to use that base e instead. Okay, so it's because we're given the rate of growth, that tells me we're using this formula instead this time. Then we're going to do our rate. Well, remember, we want to convert our rate to a decimal. So 40% is just going to be 0.40 or 0.4. So we're going to have 0.4. And then we need our t in there. So there's our model. All right, now we want to know the estimated count after 10 hours. Okay, well, t was measured in hours. They're giving us a number of hours. So we just got to substitute that in this time. So we're looking for n of 10. That's going to be 500 times e to the 0.4 times 10. Now, again, you could just go ahead and put that in the calculator if you want to. You could simplify the exponent first if you prefer. So we have 500 e 0.4 times 10 is just 4. Now, at that point, I do have to go to the calculator, right? Because e to the 4th power is going to be a decimal anyway. So we can just do 500 times e to the 4th power. When we do that, we should get 27,299. And then 0.07, or in this case, I'm just going to round to the nearest number of bacteria. And so this is that many bacteria. All right, now our next question, we want to know after how many hours will the bacteria count reach 80,000? Okay, so they're giving us the total count of bacteria this time. They're asking for how many hours, so we're looking for a t value. We're going to set our equation equal to 80,000 this time. We still know the initial population is 500. We have E, our growth rate still 0.4, and we're looking for T. So again, first step, let's get the E by itself. So we're going to divide by 500. So we take 80,000 divided by 500, gives us 160, equals E to the 0.4 T. Now we need to use a logarithm to get the T out of the exponent. This time the natural log definitely makes the most sense because our base is E. We're going to take the natural log of 160 equals natural log of E to the 0.4 T. Remember, at that point, we have natural log of 160, and our properties of logarithms say if we take natural log of E to some power, we're just going to get the exponent, so that becomes 0.4 T. And now we can divide both sides by 0.4, so we have natural log of 160 over 0.4 is equal to T. Again, that would be an exact value, but in general, when we're talking about an amount of time here, you probably would prefer the decimal just so you know about how long it's actually taking. So if we do natural log of 160 divided by 0.4, that tells us that our T value is equal to 12.69. Again, don't forget your units here. So our time this time was measured in hours. So this is 12.69 hours for our bacteria count to reach 80,000. All right, and then again, our last piece here, we want to sketch the graph. Again, I'm going to go to Desmos to do this, just so we can look at it together. All right, so this time, again, I'm just going to use y instead of n of t equals, we've got 500 as our initial population, e as our base, and we've got 0.4, and again, I'm going to use x instead of t. Now, the window that we used last time actually works pretty well for this one too. We can see that initial population of 500 right here, so that's our y-intercept. It is an exponential growth problem, so it's still that J-shaped curve. And you can see, right, that we were trying to reach a population of 80,000, and we said that would take 12.69 hours, so that's well off of our screen because this thing is growing very, very rapidly at that point. So just notice here that our doubling time formula and our rate of growth formula, as long as we have exponential growth in both cases, it's still going to be that J-shaped curve. They're very, very similar to each other, okay? All right, now example 4, we want to actually compare some different rates of population growth just to see how much of a difference it could make. Okay, so in 2000, the population of the world was about 6.1 billion, and the relative rate of growth was 1.4% per year. It's claimed that the rate of 1% or 1.0% per year would make a significant difference in the population in just a few decades. So we want to test this claim. We're going to estimate the population in the year 2050 using 1.4%, which is what they think it was rising at, and then we'll change it to 1.0% instead just to see how much of a difference in the predicted population that would make. Okay, so first off, we need our formulas, right? So we're going to say in this case, we got n of t equals, we're starting here with an initial population in the year 2000 of 6.1 billion. I'm just going to go with 6.1. I don't want to actually write out the billion part right here. We'll just have to remember that whatever we get as our population is measured in billions now. Now, we're given a growth rate, which tells us we're using the formula with the E in it. And then we actually need our rate of growth this time. Okay, so when we do our rate of growth, this time it's only 1.4%. And so if we convert that to a decimal, that's going to be 0.014. We got 0.014 times t. Right, so that's our model now for what we think the relative rate of growth is at 1.4%. Now we want to actually estimate what the population would be in the year 2050. So to do that, we need a t-value. We'll notice here we're starting in the year 2000. We're going to the year 2050. That's a 50-year difference. So that's going to be our t-value this time. So we're looking for n of 50. So we have 6.1 times e to the 0.014 times 50. And again, I'm just going to go straight to my calculator here and put that in there. So if we do 6.1 times e, 0.014 times 50, that should give us 12.28. And remember, this was in billions now. And this was a population of people on Earth, right? So I'll also include that this was people. Okay, so 12.28 billion people is what we would estimate the population to be in the year 2050 if our growth rate is 1.4%. I'm going to do the other one down here at the bottom just so I have space. This time we want to use a relative rate of growth of 1.0% instead, right? So our formula here now is going to be n of t equals, still starting with 6.1 billion people. E is still our base, but now our R value is going to be 0.01 instead. So we have 0.01 times t. So when we substitute in now, we're still using 50 because we want to know the population in the year 2050. So we have 6.1 times e to the 0.01 times 50. So if we do that now, 6.1 times e to the 0.01 times 50, that's going to give us 10.06 if we round that to 2 decimal places. And again, our units are still the same. This is still in billions of people. And so 10.06 billion people. So notice here, right, that after 50 years, our estimate of the population on Earth is over 2 billion people different if we use a 1.4% rate of growth versus a 1.0% rate of growth. So you might think, oh, well, it's only 0.4%, right? It's a very small rate. But when you're talking about such a large population over a 50-year time period, it can make a significant difference in your estimates, right? And so that's why it's so important that scientists figure out what these percentage rates of growth are and are pretty accurate in those percentage rates of growth so that we can actually make these predictions much better, right? Because 1.0% would not be accurate enough if the true population growth is 1.4% instead. Okay. Now, the next piece says we want to graph both of these in the same viewing rectangle, over the next 100 years. Okay, so I'm going to put both of these in Desmos now so that we can actually see what the graphs look like and compare them. We're going to look at 100 years. Okay, so we got 6.1 times e to the 0.014. I'm going to use x here. Then the other one's going to be 6.1 times e to the 0.01 x instead. Now this time, because I'm using 6.1 instead of 6.1 billion, that's why we're going to have to actually adjust our window down in terms of the y values. Okay, so I'm going to bring this down now. We'll go with 100 for right now, or actually, sorry, 10 works. And we might have to adjust that out once we actually get beyond what we need. This time, the x value, though, we want to look at 100 years, okay? And that's our t value, or our x value for this one. I'm going to bump that up to 100. Right, and you can see that that does go off screen now. We already knew at 50 years we were at 10 billion and 12 billion, so we're going to have to go up a little bit. So I'm just going to bump this to 20 just to see if that's big enough. And you can see that for one of ours, 20 billion actually takes care of it, but for the other graph, it goes even beyond that. Let's go ahead and bump this to 30. Now we can see, right, that's what our graph looks like. So even though they start, right, at our initial time at the same amount, 6.1 billion people, that difference in our rate of growth of just 0.4%, right, 1.4 versus 1, gives us a significant difference now once we get out towards 100 years, because you can see, right, like this point here, I'm almost at 100 years, is already at 16.4 billion. But then if we go out here now, right, these points out here are already in the 20s, right? So 24 billion people instead. Right? So once we go, even beyond 50, now we're at an 8 billion difference between our two populations once we get closer to 100 years. All right. Example 5. So a culture starts with 10,000 bacteria and the number doubles every 40 minutes. We want to find a function, n of t equals n sub 0 times 2 to the t over a, that models the number of bacteria after t hours. Okay, so in this case, we're going to find that doubling time formula, the first one we looked at. So let's think about what we know. Well, we start with 10,000, so this is going to be our n sub 0. That's our initial population. And we know we're doubling every 40 minutes, so that's going to be our a value. So if I set this one up now, notice here that we want our t value measured in hours. So the first thing we're going to have to do is get that a value in the same units. Well, to do that, I'm starting with 40 minutes. Now I want to convert that into hours. So I'm going to multiply here. I need to cancel out minutes. I need to get to hours. So I know for every 1 hour, there's 60 minutes. Minutes cancel out. So that's going to give us 40 over 60, or 2/3 hours. Okay. So that tells me my a value now in terms of hours is going to be 2/3 instead. So when I set this one up, I have n of t equals our initial population of 10,000 times 2 to the t divided by 2/3. Now remember, when we divide by a fraction, we're really just multiplying by its reciprocal. I'm going to rewrite this now as n of t equals 10,000 times 2 to the 3/2 t. So instead of dividing by a fraction and having a fraction within a fraction, I'm going to multiply by its reciprocal. So that's just going to give us 3/2 times t now as our exponent. So there's our function now that models the number of bacteria after t hours using that doubling time formula. Now we want to find a function N sub 0 times e to the RT that models the number of bacteria after T hours. So that means we need to find the relative rate of growth. Well, to do that, we need to use that doubling time formula to kind of give us an idea of what we're doing, right? So we know in this case that we're doubling every 40 minutes. So if I can figure out how many bacteria I would have after it doubles, then I could actually set this up and find that relative rate of growth, right? So I need to know how much time it's going to take to double and then use that to actually find the rate of growth. Well, I know it takes, in this case, 2/3 hours to reach that rate of growth. And I know if I double my population, it's going to be 20,000 because I started with 10,000. So I'm going to set this up as 20,000 equals 10,000 times E to the R times, and then I'm going to put in here the amount of time it takes to double, which again, in terms of hours, was 2/3 hours. So this would be 2/3. Again, since I already know what my doubling time is, and I know what double my initial population would be, I can put double the population in as my N of T, keep my initial population the same, use my doubling time as the T value now, and now we can just solve for the rate. So first step, I'm going to divide by 10,000. That's going to give us 2 equals E to the 2/3 R. Now I'm going to take my natural log of both sides. So we have natural log of 2 equals the natural log of E to the 2/3 R. Remember, this is just going to give us the exponent now when I do this. Now we're left with natural log of 2 equals 2/3 R. And if I divide by 2/3, same thing as multiplying by 3/2. So we're going to have 3/2 natural log of 2 equals R. Or if you prefer the decimal, right, we can actually round that off. So if we do 3/2 times the natural log of 2, it's going to give us about 1.04 as our rate. Now, we can't stop there because we actually want the function itself, right? Not just the R value. So now I'm going to come back and I'm going to write what the actual function would be. So we have N of T equals N sub 0, which is our initial population of 10,000, E to the 1.04 times T. So that would be our function now in that form using the actual rate of growth. So even if you're given a doubling time, right, we talked about the fact that these two functions graphically are very similar, right? They're both J-shaped curves, they're exponential growth. So we can actually write one in terms of the other. It's just a matter of finding that R value if it's not given by using what we know about the doubling time now. And I'm not going to go over to Desmos because I think we've done enough of these graphs now that you can see what that graph looks like. Just know that if you were to graph either one of these functions now, they should look exactly the same. Obviously, the second one, because we rounded that 1.04t off a little bit, might not match up exactly to the first one, but they're going to be very similar, right? They have the same initial. The doubling time and the rate of growth here should match. And so if you were to graph these, they should line up almost exactly. If you were to keep all the decimal places for your R value, then they would be exactly the same. All right, now radioactive decay. So everything we've looked at so far has been growth. Now we're going to look at what something is decaying instead. So if M sub 0 is the initial mass of a radioactive substance with a half-life of h, the mass remaining at time t is modeled by the function M of t equals M sub 0 times e to the negative RT. So notice here now our rate is negative because it's decaying instead of growing, right? That's really the only difference in our previous formula and the one we have now. Now, if you're given half-life, which is the opposite of doubling time, right, then we can actually calculate that rate using this formula right here. So instead of actually having to have two different formulas, one for the half-life and one using our rate of decay, we can actually say, well, let's just use the rate of decay formula. If we know the half-life, now we can substitute it into this. That'll give us our R value, and we can use that with this formula now. Okay, so our decay rate is going to be the natural log of 2 divided by whatever the half-life is, and then we can just substitute that into this formula up here. All right, so polonium-210 has a half-life of 140 days. So we want to suppose that a sample of the substance has a mass of 300 milligrams and find a function m of t equals m sub 0 times 2 to the negative t over h that models the mass remaining after t days. Okay, so in this case, that's the half-life formula using the half-life and the time, and then we're going to rewrite it using the rate instead. Okay, so we're going to write it in both forms. So for this first one here, we're going to start with m of t. We know our initial mass this time is 300 milligrams. So we're going to start with that. Our base needs to be 2. And again, because it's a half-life, it's decaying. Now we're going to have a negative instead of a positive in our exponent. So it's going to be negative t divided by, and then we need our half-life. In this case, we want that to be in days. Our half-life was given in days, so we don't need to do any conversions. So that's just going to be 140 there. So notice the only difference now between our half-life formula using the actual half-life and our doubling time formula is that our exponent is a negative instead. Okay, so we still use a base of 2, we just use a negative exponent. Now the next piece here, we want to get this into this other form. Okay, so we need to know the rate of growth. Remember, we have the formula from the last slide that says that our rate of growth is equal to the, or rate of decay, sorry, is equal to the natural log of 2 divided by the half-life, which in this case is 140. So we're going to take natural log of 2, divide that by 140. And if we do that, we should get 0.005. If you wanted to keep more decimal places than that, you could. So let's actually go out a little bit further just because we have so many zeros at the front here. So we'll go with 0.495 instead. And just remember, right, generally in WebAssign, it tells you how many decimal places to keep. And I'll try to be sure to include that on the test as well, just so you know what to round to. Okay, so now if we actually write this one out, we're going to have m sub 0, which is our 300 milligrams, times e. Remember, our exponent now, because it's decay, is going to be negative. Then we have our decay rate, which is 0.00495 times t. So those are the two different forms. And again, both of these equations will work to model this situation, right? One just uses the 2 as the base, the other uses the e as the base, but they will give you the same values if you were to substitute amounts of time in. All right, so now we want to find the mass remaining after 1 year. Well, notice here, we need our t value to be measured in days because that's what we were actually using in our functions above. And so we're going to have to use a t value here of 365 since there's 365 days in a year. Remember, we said that's always going to be the case no matter what, right? We don't worry about leap years and 366 days. We're always just going to use 365 for our t in that case. And so it does not matter, like I said, which of these two functions you use, because they should both give you about the same amount. Obviously, we rounded off this decimal value here, so it might be slightly different, okay, but it really shouldn't matter. So I'm going to go ahead and use the second one. M of 365 is equal to 300 times e to the negative 0.00495 times, and then we're substituting 365 in for t. And again, we'll just go to our calculator for that. So 300 times e to the negative 0.00495 times 365. If we do that now, that should give us 49.256. In this case, remember, we're talking about a mass of this substance. So having decimals here is perfectly fine, right? So we'll say that this is in milligrams now. So that's how much would be remaining after 1 year. Now, always be careful with these, right? A good way to think about it is we know we started with 300, we know we're decaying, and we know every 140 days it's going to reach half of what it was previously, right? So in this case, 49 actually makes sense because half of 300 would be 150. That would take 140 days. After another 140 days, it would be half of that, which would put it down to, in this case, 75. And then after another 140 days, it will be half of that. We haven't quite gotten there at 365 days, so we're not quite at half of 75 at that point, okay? Now the next question is we want to know how long will it take for the sample to decay to a mass of 200 milligrams? So again, I'm going to use my formula, same one we just used. I'm going to set it equal to 200 this time though. We got 200 equals, initial is 300, e to the negative 0.00495 times t, because we're looking for the amount of time. Same steps as all the other ones we've done so far. Divide by the 300. That's going to give us 2/3 equals e to the negative 0.00495 t. Then we can take our natural log of both sides. So we have natural log 2/3. Remember, when we take the natural log of this one over here, it's just going to give us the exponent, negative 0.00495 t. And now we divide, so we end up with natural log of 2/3 over negative 0.00495. And again, that's an exact value, other than the rounding of the decimal that we have in the denominator already. Okay, but let's go ahead and find an approximation for that amount of time now. So if we do that, this tells us that t is 81.9. And again, don't forget your units here. Okay, since our t value was measured in days, this is actually 81.9 days for us to get to 200 milligrams. And again, always think about whether your answer makes sense. We know in this case that we did decay, right? We started with 300, we ended up at 200. Our half-life, though, would put us at 150, and that would take 140 days to get there. So it didn't take us that long to get to 200 because we didn't go all the way to half of what we started with. So 81.9 days does make sense here. Okay, now I will graph this one, right, because this is different from the ones we've looked at so far. Switch over to Desmos. So I'm going to do y equals. I'm going to graph the second one since that's kind of the one we've been working with the most. So we'll do e to the negative 0.00495 times x. Now, again, keep in mind what our units are here. We know we're starting with 300. That's our initial. I'm going to go ahead and bump up the y maximum just to 500, just so I can at least see that y-intercept. And you can see in this case, we're probably going to want to go a little bit further out along the x-axis too, so we can really see what's going on here. I'm just going to make that 1,000 instead. And so we can see that starting value there of 300, that was our initial mass. Notice this time we have an L-shaped curve, right? Because we are decaying, the radioactive substance is going down instead. And so every 140 days, we know it's going to be half of what it was before. And you can kind of see that here, that when we get to 140, let's see if I can get right on that, there's your 150, right? So that will be half of 300 that we started with. And then every 140 days, it's going to be half of what it was the previous 140 days. Notice here, right, that we still have that horizontal asymptote at 0. This thing is never going to go away, right? So it continues to half every 140 days, but getting to half of what it was previously is still never going to get you all the way to 0. All right, now Newton's law of cooling. Okay, so this is our last application of our exponential growth and decay. So if D sub 0 is the initial temperature difference between an object and its surroundings, and if its surroundings have a temperature of T sub S, then the temperature of the object at time T is going to be modeled by this function. Okay, so we have our temperature surroundings plus the difference in temperature times e to the negative kt. The k here is going to be a constant value that depends on the object, right? Because if you think about it, certain objects are going to cool differently, right? Metal objects are going to cool differently from like a liquid like water or something. Okay, so you're going to have to know what object is actually cooling and what its constant is that it's cooling at. Okay, and then T in this case again is time, and that could be measured in anything. It just depends on the context of the problem. All right, so we've got a cup of coffee, has a temperature of 200 degrees Fahrenheit, and is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees. We want to find a function that models the temperature of the coffee at time t. So we're going to use that Newton's law of cooling formula we just saw, substitute everything we know in there to get this function in terms of t now. All right, so we go back. We know it's going to be T of T, right? Temperature at a certain time. So I'm going to start with that, because that's going to be our model. Now, the first piece of this is going to be T sub S. Well, that's the temperature of the surroundings. So if we look here, we know that our surrounding temperature, the room temperature, is going to be 70 degrees Fahrenheit. So this gives us T sub S. So we're going to start with 70 plus. Now the next piece of our formula is D sub 0. That's the initial temperature difference between an object and its surroundings. So we need to know what's the temperature difference now between the object that's cooling and the surrounding temperature. Well, the object that's cooling is the coffee, that's 200 degrees Fahrenheit, and our room temperature now is 70 degrees. So I'm actually going to subtract those so that I know what the temperature difference is. And so our D sub 0 now is actually 130. So you actually have to do some work to actually find that temperature difference, because you're looking at what's the difference in temperature between the object and its surroundings. We're going to use 130. And the next piece here, we're going to do e to the negative k times t. We're going to have e. Now, I don't know what my k value is this time. They don't give us that constant. So this is going to be negative k and then times t. Now, we're going to need to know the k value, right? That's kind of our goal at this point. So we have to think about the other information that's given to us. Well, they tell us that after 10 minutes, the temperature is 150 degrees. Well, that gives me a T of T value, and it gives me a T value. So I know my T is 10 minutes. I know T of T. So my temperature after 10 minutes is going to be 150. So now I can substitute those in and actually try to solve for that K value. We're going to have 150 equals 70 plus 130 times e to the negative k times 10 minutes. Now we need to solve for that exponent. We need to know our k value. So I'm going to subtract 70 here. That's going to give us 80 equals 130 times e to the negative 10k. Then I'm going to divide by 130. And give us 8 over 13 equals e to the negative 10k. Take your natural log on both sides. So we have natural log of 8 over 13 Remember, taking the natural log over here now is just going to give you the exponent, negative 10k. And then we divide both sides by negative 10. And so if we find a decimal value for that now, we can just do natural log 8 over 13 divided by negative 10. And that's going to give us 0.0486. So now we're going to take that k value, we're going to substitute it back into our formula. And so this is going to give us T of T equals 70 plus 130 times E to the negative 0.0486 times T. So that would be our function this time to model that cooling situation. And again, temperature is decreasing. That's why we have a negative exponent in this case. Okay, now we want to find the temperature of the coffee after 15 minutes. So we're going to use that function that we just created. This is measured in minutes, and so is our T value at the top here. So we can just substitute this in. So we're going to have T of 15 equals 70 plus 130 times E to the negative 0.0486 times 15. And again, I would just go straight to my calculator here, substitute all that in there. And if we do that, we should get about 133 degrees Fahrenheit. So again, don't forget your units. We are dealing with temperature, and it's measured in degrees Fahrenheit for this problem. And again, as always, make sure your answer makes sense. We started at 200 degrees. We are cooling. We're cooling for 15 minutes. And so the fact that we get down to 133 degrees makes sense. Remember, at 10 minutes, we were already down to 150, so we should be less than that after 15 minutes. That 133 does make sense. Now we want to know, after how long will it have cooled to 100 degrees Fahrenheit? So that's our new temperature now. We're going to have 100 equals 70 plus 130 e to the negative 0.0486 times t. So we're looking for our t value this time. First step, we're going to subtract the 70, move it to the other side. So that's going to give us 30 equals 130 e to the negative 0.0486 t. Now we divide by the 130. That's going to give us 3 over 13 equals e to the negative 0.0486 t. Take your natural log of both sides. So now we have the natural log of 3 over 13. So I'm going to move this down here. Natural log of 3 over 13 equals, again, that's just going to give us the exponent, negative 0.0486 times t. And now we divide. We have natural log 3 over 13 divided by negative 0.0486. That is our t value. And so again, we go to our calculator and just get a decimal for that. If we do that, we should get about 30.2. Again, always keep in mind your units here. So we're finding a t, a time value. Our time this time was measured in minutes. So that tells us that after just over 30 minutes, our temperature will have cooled to 100 degrees Fahrenheit. And again, I'm not going to take the time to switch over to Desmos to show you the graph of this, right? We could graph it just like the previous one. It is going to be a cooling problem, so it is going to be decreasing. So you'll see that L-shaped curve if you were to do this one now. All right, so that's all we've got for that section. As always, send me those questions in WebAssign as you have them. Come see me during student hours if you need to. Have a great day, and I will see you next time.